Welcome. This lecture is about one of the most consequential decisions in experimental design, choosing your design structure before a single observation exists, and then being completely honest about what that structure cannot tell you. We will work through every step: budgeting degrees of freedom, selecting generators, deriving the full alias structure, analyzing the data, and writing a formal ambiguity report, using a single running example that ties everything together. Here's the fundamental tension you face every time you plan a fractional factorial experiment. You must commit to a run structure: which generators to use, what resolution you will achieve, which effects will be aliased with which, before you have collected any data at all. That is not a flaw in the method. It is the nature of designed experiments, but it means the decisions you make at the planning stage determine the quality of every inference you will draw later. There are two situations you will encounter in practice. In the first, the run budget is fixed. The client has 16 runs, or 32, and that is that. Your job is to extract the maximum resolution from that fixed number of runs. In the second situation, the budget is flexible, and your job is to find the smallest design that leaves the effects you care about unconfounded. Both situations demand the same discipline. You must work out the alias structure explicitly before you bake a single loaf or run a single reaction, because once the data are collected, the aliasing is locked in. Let me introduce the example we will use throughout this lecture. A food science team wants to understand what drives bread loaf volume in a pilot bakery. They have identified 7 factors: oven temperature, humidity, mixing time, flour type, fat level, leavening amount, and resting time. They want to study all 7, but the pilot bakery can only support 16 runs before the study budget is exhausted. 16 runs for 7 factors means a 2 to the 7 minus 3 design, a 1/16th fraction of the full factorial. 3 generators will be needed. The team must choose those generators before any baking begins, and the choice will determine everything about what they can and cannot learn. That is the problem we are going to solve. Before we discuss how to choose generators, let me show you the actual design matrix the team will use, so you can see concretely what a 16-run, 7-factor experiment looks like. Each of the 16 rows is one baking run. The columns labeled A through G are the coded factor levels: -1 for the low setting, +1 for the high setting. The final column is the loaf volume in cubic centimeters, which is what the team will measure. Now look carefully at the structure. Columns A through D are the base factors. They are assigned freely, cycling through all combinations of their levels in a standard pattern. Columns E, F, and G are not freely assigned. Their levels in every row are determined by the generators we choose. That dependency is the alias structure made visible. E, F, and G are functions of A through D, which means any effect involving E, F, or G is entangled with effects involving A through D. The volumes you see, ranging from around 1665 to just over 2005 cubic centimeters, are the responses the team will analyze. Keep this matrix in mind. We will return to these numbers repeatedly. Now let us talk about why 16 runs forces 3 generators and not 2 or 4. The key concept is the degrees of freedom budget. When you have n runs, you have exactly n-1 estimable contrasts. 1 degree of freedom is consumed by the overall mean, and the remaining n-1 are available for effects. That is your budget, and you cannot spend more than you have. On the other side of the ledger, think about what you want to estimate. With k factors, you have k main effects. You also have k choose, 2-factor interactions, every pair of factors. For 7 factors, that is 21 2-factor interactions. So if you want to estimate everything through two-factor interactions, you need at least 28 degrees of freedom. The connection to generators is this. Each generator you add halves the number of runs. A 2 to the k design has the full 2 to the k runs. Add one generator and you get a half fraction 2 to the k minus 1 runs. Add a second and you get a quarter fraction. Add a third and you get an eighth fraction. Each generator also doubles the number of aliases per estimated contrast. With p generators, each contrast you estimate is actually the sum of 2 to the p effects. So the choice of p is not arbitrary. It is forced by the arithmetic of your budget. Let us apply this arithmetic to the bread experiment. With 7 factors and 16 runs, the degrees of freedom available is 16 minus 1, which is 15. The degrees of freedom needed to estimate all main effects and two-factor interactions is 7 plus 21, which is 28. 28 is nearly twice 15. There is no way to fit all those effects into 16 runs without aliasing. So how many generators do we need? A 2 to the 7 minus 1 design would give 64 runs, far more than 16. A 2 to the 7 minus 2 design would give 32 runs, still twice the budget. A 2 to the 7 minus 3 design gives exactly 16 runs. 3 generators is the only option, and with 3 generators, each estimated contrast carries 8 aliases. The contrast you compute is actually the sum of 8 effects, only one of which you can attribute with confidence. The next step up, a 2 to the 7 minus 2 design with 32 runs, is a different experiment entirely, one the team cannot afford. The arithmetic is unambiguous, and it is worth sitting with for a moment. 15 degrees of freedom available, 28 needed. The gap is not close. 3 generators, 16 runs, 8 aliases per contrast. Notice what this table also tells you about the next larger fraction. 32 runs would give 31 degrees of freedom, still not enough to estimate all 28 effects cleanly, but much closer, and with a different alias structure. The team's budget decision, 16 runs, is not just a cost decision. It is a scientific decision because it determines the resolution they can achieve and the ambiguities they will have to live with. Understanding this before the experiment runs is the entire point of the degrees of freedom budget. Now that we know 3 generators are required, the question becomes, which 3 generators should we choose? This is where resolution enters the picture. Resolution is defined as the length of the shortest word in the defining relation, and I want to make sure that definition lands as something meaningful, not just a formula. The defining relation is the set of all products of generators, including the generators themselves and all their cross products. Every word in the defining relation represents a set of effects that are completely confounded with the identity, meaning they cannot be distinguished from each other at all. The shortest word tells you the most severe confounding in the design. If the shortest word has length 3, a main effect is aliased with a two-factor interaction, that is resolution 3, and it is quite limiting. If the shortest word has length 4, main effects are aliased only with three-factor interactions, and two-factor interactions are aliased with each other. That is resolution IVs, which is much more useful. Length 5 means main effects are clear of all two-factor interactions, and two-factor interactions are clear of each other. That is resolution V, the gold standard. The practical implication is this. When you have P generators, you do not just get P words in the defining relation. You get 2 to the P minus 1 words, because you must include all pairwise products of generators, all triple products, and so on. With 3 generators, that is 7 words. The shortest of those 7 words determines your resolution, and the choice of generators determines which words appear. So generator selection is the lever you pull to maximize resolution. To make this concrete, let us compare 2 candidate generator sets for the bread design. Both use 3 generators. Both give 16 runs. The question is, which one achieves higher resolution? The naive set assigns E equal to ABC, F equal to BCD, and G equal to ACD. The better set assigns E equal to ABD, F equal to ABC, and G equal to ABCD. These look similar, but the words they generate can be quite different. To find out, you compute all 7 words, the 3 generators themselves, the 3 pairwise products, and the 1 triple product. Then you find the shortest word among those 7. Whichever set produces the longer shortest word wins. That is the higher resolution design. Look at what the comparison reveals. Every word in the naive set has length 4. Every word in the better set also has length 4. Both designs achieve resolution IV. Now, this is actually a reassuring result. It means the naive labeling was not as bad as it might have been. But the lesson is not that generator selection does not matter. The lesson is that you must check. In many practical cases, a careless generator choice will produce a word of length 3, dropping you to resolution 3. The only way to know is to enumerate all 7 words and find the minimum. Here, both sets happen to achieve resolution IV, so the team can use either. In practice, you would also look at the specific alias chains, which 2-factor interactions are aliased with which, to choose the set that keeps the most scientifically interesting pairs separated. But the resolution check comes first, and it must be done explicitly. Resolution IV is good, but it is not the best possible outcome. Let me introduce the concept of free and clear, because it is the criterion clients often actually want, even if they do not know to ask for it by name. A design is free and clear when no main effect is aliased with any 2-factor interaction, and no 2-factor interaction is aliased with any other 2-factor interaction. That requires resolution V at minimum. At resolution IV, main effects are clean. They are aliased only with 3-factor and higher interactions, which we can usually dismiss under effect sparsity. But 2-factor interactions alias each other. That means if you find a large 2-factor interaction contrast, you cannot tell which of the aliased pairs is responsible. Free and clear eliminates that ambiguity entirely. In practice, the question of whether to pursue free and clear is a conversation with the client. If the scientific question requires estimating all 2-factor interactions independently, if the client genuinely needs to know whether temperature interacts with humidity separately from whether mixing time interacts with flour type, then resolution IV is not sufficient, and you need to say so before the experiment runs. Can the bread team achieve free and clear in 16 runs? The answer is no, and the arithmetic shows why immediately. Free and clear requires resolution V, which means the shortest word in the defining relation must have length at least 5. To achieve that with 7 factors, you need enough degrees of freedom to estimate all main effects and all 2-factor interactions without aliasing. That requires at least 28 degrees of freedom, which means at least 29 runs. And since fractional factorials come in powers of 2, the minimum is 32 runs, a 2 to the 7 minus 2 design. 16 runs simply cannot deliver free and clear for 7 factors. This is not a failure of creativity in choosing generators. It is a mathematical impossibility. The team's 16-run budget locks them into resolution IV at best, with every 2-factor interaction aliased with at least one other. The honest thing to do is to state this clearly before the experiment begins, so the client understands what the design can and cannot deliver. This table makes the trade-off completely explicit, and it is exactly the kind of summary you would include in a pre-experiment report to a client. The 16-run design achieves resolution IV. Main effects are clean, but two-factor interactions are not, and free and clear is not achievable. The 32-run design achieves resolution V. Everything is clean, and free and clear is delivered. The full factorial with 128 runs achieves resolution 7, but that is almost never the practical choice. The key message here is that the run count is not just a budget number. It is a scientific commitment. When the team says they have 16 runs, they are also saying they accept that two-factor interactions will be aliased with each other. A practitioner's job is to make that trade-off visible and explicit, so the client can decide whether the budget is truly fixed or whether the scientific question demands more runs. If the client insists on 16 runs, you proceed with resolution IV and you document the aliasing. If the client can be persuaded to double the run count, you achieve free and clear. That conversation should happen before any baking begins. Now let us talk about how to actually derive the alias chains, because the alias structure is not just the theoretical property of the design, it is the practical tool you use to interpret every result. Here is the mechanism. The defining relation is a set of words, including the identity. To find the alias chain for any effect X, you multiply X by every word in the defining relation. Each product gives you one alias. The full chain is the complete list of effects that are estimated jointly by the contrast for X. Why does this work? Because in a fractional factorial, the columns for aliased effects are identical. They have the same pattern of +1s and -1s across all runs. When you compute the contrast for X, you are computing the same linear combination that you would compute for any of its aliases. The data cannot distinguish between them. The alias chain is the mathematical statement of that indistinguishability. In practice, at resolution IV, the alias chains for main effects contain only three-factor and higher interactions. Under the assumption of effect sparsity that higher-order interactions are negligible, you can attribute a large main effect contrast to the main effect itself with reasonable confidence. The alias chains for two-factor interactions, however, contain other two-factor interactions. Effect sparsity does not help you there, because two-factor interactions are exactly the effects you are trying to estimate. That is why the alias chains for two-factor interactions are the ones you must report explicitly. For the bread design, with generators E equal to ABD, F equal to ABC, and G equal to ACD, the defining relation has 7 words beyond the identity: ABD, ABCF, ABD, ABCFB, DEB, BCFG, DEF, DEFG. To find the alias chain for any effect, you multiply that effect by each of those 7 words. For the main effect A, you get A times AB, DE equals BDE, A times AB, CF equals B, DEE, A times AB, CF, A times A, CD, D, G equals CD, DEF, A times ACD, D. Each product is one alias. For the two-factor interaction AB, you get AB times ABDE equals DE, AB times ABCF equals CF, and so on. Notice that the aliases of AB include DE and CF, both two-factor interactions. That is the resolution IB aliasing in action. This table is the core deliverable from the design selection phase, and I want you to read it carefully. The main effects, A through G, are each aliased with three-factor interactions like BDE and BCF, and with higher order terms. Under effect sparsity, we treat those aliases as negligible, so a large main effect contrast can be attributed to the main effect with reasonable confidence. Now look at the two-factor interaction rows. The contrast for AB is aliased with DE and CF, both two-factor interactions. The contrast for AC is aliased with BF and DG. Every single two-factor interaction contrast is aliased with at least two other two-factor interactions. There is no two-factor interaction that can be estimated cleanly from this design. This table should be produced and reviewed before the experiment runs. It tells you exactly what questions the design can answer cleanly and exactly where ambiguity will remain. A practitioner who delivers this table to a client before the experiment is doing their job. A practitioner who discovers the aliasing only after the data are collected has missed the most important step. With the alias structure in hand, we are ready to analyze the data. The approach for a fractional factorial is straightforward in concept, even though the interpretation requires care. You fit a model that includes all the main effects, all 7 in the bread case, and you compute the estimated effect for each one. Each estimated effect is a contrast, a weighted sum of the observed responses. The key tool for identifying which contrasts are meaningfully large is the half-normal plot. Here is the idea behind it. If all effects were truly zero, if the response were pure noise, the estimated effects would be random, centered near zero, and their absolute values would follow a half-normal distribution. On a half-normal plot, you plot the absolute values of the estimated effects against the quantiles of a half-normal distribution. Effects that are consistent with noise fall along a straight line to the origin. Effects that are genuinely active, that reflect real factor influences, will be larger than noise predicts, and they will pull away from that line. The practical rule is, label the points that depart clearly from the reference line. Those are your active contrasts, and remember, each labeled point is not a single effect. It is an alias chain. The contrast is large. Which member of the chain is responsible is a separate question that requires domain knowledge and, sometimes, follow-up experiments. The task here is to fit the main effects model to the 16 bread observations and produce the half-normal plot. The estimated effects are computed as contrasts. Each one is the average response at the high level of a factor minus the average response at the low level, divided by 2. The half-normal plot then orders those absolute values and plots them against the expected order statistics of a half-normal distribution. Points that lie along the reference line are indistinguishable from noise. Points that lift off the line are the active contrasts, the ones worth interpreting. The labeling on the plot will tell us which contrasts to look up in the alias table. The half-normal plot is a visual summary of where the signal is. Points along the dashed reference line are consistent with random variation. They could easily be noise. The points that depart from that line, the ones that are labeled, are the contrasts that are too large to dismiss as chance. Notice that we label the estimated contrast by its primary effect name, AE, and the two-factor interaction chains, not by a single definitive effect. That labeling is deliberate. The contrast for A is large, but what we are really saying is that the alias chain anchored by A is active. The contrast for E is large, meaning the alias chain anchored by E is active. And the two labeled two-factor interaction contrasts are large, meaning those alias chains are active. The next step is to go to the alias table and read out exactly what is in each of those chains. When a contrast is active, the design gives you a number, an estimated effect size, but it does not tell you which member of the alias chain produced that number. That is the fundamental limitation of a fractional factorial, and it must be stated explicitly. The formula makes this precise. What you estimate is not the effect of AB alone. What you estimate is the sum of the effect of AB plus the effect of DE plus the effect of DE plus the effect of CF plus all the higher order aliases. If that sum is large, any one of those two-factor interactions could be responsible, or several of them together. The data alone cannot separate them. This is not a failure. It is an honest statement of what the design can and cannot do. The practitioner's job is to report the ambiguity explicitly. Here is the active contrast. Here is its alias chain. Here are the effects that cannot be separated. And here is what you would need to do to resolve the ambiguity. That is the ambiguity report, and it is as much a deliverable as the point estimates themselves. Let us now draft the formal ambiguity report for the bread study. For each active contrast, we need three things: the alias chain, a statement of which effects cannot be separated, and a specification of the minimal follow-up experiment that would resolve the most consequential ambiguity. For the main effects, the alias chains contain only three-factor and higher interactions. Under effect sparsity, we attribute the large contrast to the main effect itself. For the two-factor interaction contrasts, the chains contain multiple two-factor interactions, and we cannot attribute the signal to any one of them without additional data. The most common follow-up strategy is a foldover. A foldover on a specific factor reverses the signs of that factor's column across all runs, which breaks certain alias chains while preserving others. If the team suspects that the AE interaction is the active one in the chain that also contains BF and CG, a foldover on A would separate AE from BF and CG. That is the targeted follow-up. This table is the complete ambiguity report, and I want to walk through it carefully because this is what you actually deliver to a client. The first row is the contrast for A oven temperature. The estimated effect is 57.7 cubic centimeters. The alias chain contains only three-factor and higher interactions, so under effect sparsity, we attribute this cleanly to oven temperature. No follow-up is needed for this one. The second row is the contrast for E fat level. The estimated effect is 46.2 cubic centimeters. Same story, the alias chain is clean under effect sparsity, and we attribute this to fat level. Now look at the third row. The estimated contrast is 36.9 cubic centimeters, a substantial effect, but the alias chain contains AE, BF, and CG as two-factor interactions, all indistinguishable from this data. We cannot say whether it is the temperature by fat interaction, the humidity by leavening interaction, or the mixing time by resting time interaction that is driving this signal. The recommended follow-up is a foldover on a specific factor to break that alias. The fourth row is a contrast of only 2.9 cubic centimeters, small enough that, even though it is technically active, the practical significance is questionable. The alias chain contains AB, DE, and CF. We flag it as unresolved, but note that the small effect size makes it lower priority for follow-up. This is the honest, complete result. Two effects attributed cleanly, two alias chains that remain ambiguous, with specific follow-up recommendations. That is what a well-executed fractional factorial analysis looks like. Let me consolidate with the bread example demonstrated about design choices, because these lessons apply to every fractional factorial you will ever plan. The degrees of freedom budget forced 3 generators. There was no alternative at 16 runs. That was not a choice, it was arithmetic. But within that constraint, the choice of which 3 generators to use was a genuine decision with real consequences. A naive generator selection can cost you a full resolution level before you collect a single observation. Moving from resolution IV to resolution 3 means main effects are aliased with two-factor interactions, a much more severe limitation. The generator comparison we did showed that both candidate sets happen to achieve resolution IV, but that is not always the case. You must check. Generator selection is the highest leverage pre-experiment decision you make, and it costs nothing to get right. The analysis and reporting phase reinforced a different set of lessons. Resolution IV means main effects are clean, aliased only with 3-factor and higher interactions that effect sparsity lets us dismiss. But every 2-factor interaction is aliased with at least one other 2-factor interaction. That is not a footnote. It is a central feature of the design that must be communicated. Free and clear for 2-factor interactions required 32 runs, twice the budget. If the client had needed all 2-factor interactions estimated independently, the 16-run design was the wrong choice, and that conversation should have happened before the experiment. The alias chains are part of the deliverable. They belong in the results section, not in an appendix. A practitioner who reports point estimates without alias chains is giving the client an incomplete picture. Now let us give you a chance to work through this end-to-end on a new example. A chemical engineering team has 6 factors. Call them P, Q, R, S, T, and U, and 16 runs available. That is a 2 to the 6 minus 2 design, 6 factors, 2 generators, 16 runs. 2 candidate generator sets are on the table. Set A uses T equal to PQR and U equal to RST. Set B uses T equal to PQRS and U equal to RSS. Your task is to compute all the defining elation words for both sets, find the minimum word length for each, and determine which achieves higher resolution. Then, using the winning generator set, derive the alias structure, fit the model to the data, produce a half-normal plot, identify the active contrasts, and write the ambiguity report. This is the complete workflow applied to a new context. Here's the practice data set. 16 runs, 6 factors coded at +1 and -1, and a measured yield response. The structure is exactly parallel to the bread example. Columns P through S are the base factors assigned freely. Columns T and U are determined by the generators. The yield values range from about 35 to 98, a substantial spread that suggests real factor effects are present. Your first step is the generator comparison. Compute all the words for set A and set B, find the shortest word in each defining relation, and identify the winner. Then use the winning set to derive the alias structure and analyze the data. The bread example is your template. Let me walk through the generator comparison so you can check your work. For set A, with T equal to PQR and U equal to RST, the defining relation words are PQRST, RSTU, and their product PQA, CUR. The minimum word length is 4 resolution IV. For set B, with T equal to PQRS and U equal to RS, the defining relation words are PQRST, RSU, and their product PQTU. The minimum word length is 3 resolution 3. Set A wins. Resolution I versus Resolution 3 is a meaningful difference. At Resolution 3, main effects are aliased with 2-factor interactions, which makes the design nearly uninterpretable for most practical purposes. Set A's shortest word has length 4, keeping main effects clean. This is exactly the kind of result that justifies the generator comparison exercise. The two sets look superficially similar, but one is substantially better. The subtitle of this final practice slide confirms the resolution comparison. Set A achieves resolution I with a minimum word length of 4. Set B achieves only resolution 3 with a minimum word length of 3. Set A is the correct choice. The half-normal plot from the Set A analysis then identifies the active contrasts. Each labeled point on that plot represents an alias chain, not a single effect. Your final step is to look up those chains in the alias structure you derived. Apply effect sparsity and whatever domain knowledge you have about the chemistry, and write the ambiguity statement. Here are the effects that are attributed cleanly. Here are the effects that are attributed cleanly. Here are the alias chains that remain ambiguous, and here is the follow-up experiment that would resolve the most important ambiguity. That workflow. Budget the degrees of freedom. Choose generators carefully, derive the alias structure, analyze the data, and report honestly what the design cannot settle, is the complete discipline of fractional factorial experimentation. Master it, and you can design informative experiments even under severe resource constraints and deliver results that clients can actually act on.